Okay, so we're looking at the inverse normal distribution, working in reverse. So here we've got a set of data which is normally distributed. We don't know what it is, so I'm going to pretend, I probably used this example yesterday, this is how long it takes a group of people to complete a puzzle. Okay, so it's like a Rubik's Cube or something. The mean time is 20 seconds, standard deviation is 3. So I'm going to start off straight away with a sketch. Unlike the binomial distribution, I know there's no top end here. So, you know, some people just might not be very good at puzzles and might take 4 days to do it. I'm fairly sure in this case that 0 is the bottom end, although of course I'm not expecting anyone to have done it in 0 seconds, so the bottom end may well be a bit higher than that, but it's the top end, we know there's no top end. And I'm after some values, and I'm given their probabilities. So the first value I'm after is this value A, and we're told the probability that x is less than A, so the probability if someone takes less than that time is 0.75. So my first question is, because I like my sketches to be correct, where on my sketch, it'll be somewhere along this bottom axis, where on my sketch is A going to be? And specifically, is it going to be to the left of the mean or to the right of the mean? The probability that x is less than A is 0.75. What do you reckon, Grace? Where am I going to find A? Am I going to find A to the left of 20 or to the right of 20? Tell me, just remind me what that probability there is. 0.5. So if the probability of getting less than A is 0.75, it's going to have to be over here somewhere, isn't it? So I'm looking for a value there. We're told that the probability of getting a value less than something is 0.75, so it's got to be here, because it's got to be, you know, 3/4 of the values. And I'm just going to write my parameters down so I can then switch to my calculator. So it's really, really easy. All I do is go to my calculator and I go to normal distribution, but this time I go to inverse normal distribution, in N. And here we've got space for the parameters, so the standard deviation is 3, and the mean is 20, same as before. But what I'm dealing with now is a tail problem. I'm either looking at a probability that's the left-hand tail of a distribution or a right-hand tail. This is a left-hand tail. That's why my diagram's so useful. So if I hover over that, it gives me 3 options. Central isn't helpful, so it's just left or right. And then the area of that tail is 0.75. So what I'm basically asking, what value gives me a probability of 0.75? And that's my value. And as expected, it's bigger than the mean. So that gives me a little bit of reassurance that I'm barking up the right tree. Now, this isn't a probability. 0.75 is the probability. This is a number of seconds it took me to complete the puzzle. So I'm going to round it to 3 sig figs. I'm going to go back to my normal sort of rounding. So what we're basically saying is, and what the question was asking, question's asking, what's the upper quartile? That's what it's asking, isn't it? What's the value that has 75% of the results below it? That's what that question was asking. And the answer is 22. 75% of people took less than 22 seconds. And see if you can answer part B. I hope you're going to start with a little sketch. Remember, the area to the halfway point is a half, so hopefully we're looking for the value that has that's greater than that area is 0.4. So again, hopefully this will tell you where it is in relation to the peak, and also whether we're dealing with a left tail or a right tail problem. So I hope you're using the right tail option this time, because we are looking for a value that above, for greater than that value is probability of 0.4, more than a half, so less than a half, sorry. So I'm on the right tail, and the area 0.4, pretty far away from the mean. The mean's got a probability of a half for greater than that. So yeah, it's not hugely bigger than the mean. Now the third one, I don't know whether you were already puzzling over that. Unfortunately, it looks like on the calculator the central thing is going to be helpful. And I must admit, when I first saw that, I thought, great, I selected central, hoping it was going to give me a lower and an upper, but it doesn't. So the central isn't helpful. All that does is gives you symmetrical values either side of the mean. So to work out part C, we have to do it in 2 steps. So I want the probability of 16 to a particular value to be 0.3. I know 16 is below the mean. I don't actually know whether my upper value, A, is above or below the mean. And it's not actually important, so I'm going to put it there. I want that probability to equal 0.3. The way I have to do this is a 2-step process. I firstly have to come out of inverse normal mode and back into normal cumulative mode to work out this probability. So I work out the probability of 0 to 16 in this distribution. See if you can then finish off that question. So you've got to come out of inverse normal mode and go into cumulative normal mode, like we were doing last lesson, and working out the probability of 0 to 16, round that to 4 decimal places, because that's a probability. You then have to go back into inverse mode. I'll leave you to see if you can puzzle out how you go about that. So 0 to 16 gives me 0.0912. I'm looking for the value such that that is 0.3. So what I'm actually doing is using inverse normal, looking for what value there gives me a left-tailed probability of 0.3912. So I have to work out the probability of up to there, add on the probability that I'm looking for, 0.3, and then go back into inverse and do it as a left-tailed problem. As I said, I don't know at the moment whether A is above or below the mean. It doesn't make any difference. As it happens, it's below the mean, but it doesn't matter. So see if you can apply a similar principle to this question here. Remember, 1.5 is the standard deviation. So in this case, x is the diameter of the plate. So our answers are going to be diameters, so we will round them to 3 significant figures.
So when we do the areas at the 0.3912, the answer of that is A.
That's correct.
Okay.
Yeah, yeah. Yes, it's what value would give you that probability. That's what we're working with. move on to the questions I've suggested. Give everyone a chance to finish this one. Okay, so when I know 0.6 is bigger than the mean because less than, I know x is bigger than the mean because it's got a probability, the less than probability is bigger than a half. So I whacked those values in, left tail 0.6, 1.5 and 20. So yeah, as I suspected, slightly bigger than the mean, 20.4, 20.38. And then for the interquartile range, I just did a left tail of 0.25 because we're splitting the data into quarters, aren't we? So a left tail of 0.25 gave me my lower quartile. And it's always fiddly, isn't it, when you're doing calculations with these numbers. But it's that. And then my upper quartile, I could have done left tail of 0.75 or just turn it into a right tail of 0.25. That gives me and then my interquartile range is this, take away this, and because I'm rounding to 3 significant figures, I'd probably go to 4 significant figures with those values, and just one taking the other. Now, I would love at this point to say, right, let's put our feet up and have a go at those questions, and that will be fine, but I won't finish the content. So I am going to ask you to make a note of those questions so I can go on and teach the next bit. And I hope that those questions will sort of allow you to sort of practice this. Was that okay? Was there a debate going on there? Are you sure? I'm sorry, I've been often done with something. Now there is an alternative way to do this whole backwards thing. And it's not necessary because we've got these fantastic calculators. It's a bit of a throwback, but it's still on the syllabus because it gives us some interesting problems to solve. So it's more about problem solving than necessity. Before I sort of give it a title, let me give you an example of the other approach. Okay, let's say we've got some variable, and it's normally distributed. We'll stick with 20 as our mean, and we'll say standard deviation is 3. Okay, and I want to know the value x, so that I want it to have a probability of 0.025. So I'm going to draw my graph. I know my peak is at 20, and I want a value there so that that probability 0.025. And I can straight away tell you it's 26. Without looking anything up, it's 26. Is anyone able to suggest why I know it's 26? It's because of something I said or something we looked at yesterday. Let me show you the thing we looked at yesterday. Normally distributed data, it's predictable. I know that 68% of the data lies within one standard deviation of the mean. I know that 95% of the data lies within two standard deviations of the mean. So if I go 2 standard deviations up and 2 standard deviations down, I've got 95% of the data. That means I've got 5% of the data here and here, so it's 2.5% there and 2.5% there. So that's why I knew that that was 2 standard deviations above the mean. And we've got a table of values of other probabilities, because although these are the headline figures, it is predictable for other numbers of standard deviations above the mean. So let's turn to our formula book, and page 34 in our formula books. Want to see one? And so what this table gives us, page 34, is for a particular probability how far either above or below the mean that is. So this table counts for left tail and right tail problems. So actually you'll see I was wrong, wasn't I? Approximately 95% of the data lies within 2 standard deviations. If I look up in that table, P 0.025, the Z value, that's the number of standard deviations, that actually tells me it's 1.96 standard deviations, either above the mean or below the mean, depending on whether I want to work out a left tail or a right tail problem. So this table gives us, for a particular probability, how many standard deviations away from the mean it is. So is that useful? Well, it in no way replaces the calculator. I could have done that with the calculator and that would have been far easier, but it's a relic of a bygone age which for some reason has remained on the syllabus, and it does give us some quite nice problems to solve. So let's look at a couple of problems to solve. Sorry, there's the notes. Page 49, question. Page 49. Oh, yes, look. Oh, this is page 49. Page 49 and question 5. So this question doesn't start by telling us about a normal distribution at all. It just says use the percentage points table to find a value of Z. Z is what we use for how many standard deviations. A value of Z such that the probability that the big Z is greater than Z is 0.025. Well, that's what we've just done. So I'm using red for my Z values. That means that 1.96 is the number of standard deviations that gives you a probability of 0.025. 1.96 above the mean. So the answer to part A is 1.96. This value here that gives me a probability of 0.025 is 1.96 standard deviations above the mean. Then it throws in a context. It says, okay, so actually we've got a fighter jet program that only accepts the top 2.5% of candidates, and when they do the test, they find that the scores that the fighter jet trainees get are normally distributed with a mean of 80 and a standard deviation of 4. So switching to black, because I'm no longer talking about standard deviations, this is 80, and this is the value that I want, because this is the cutoff, isn't it? 2.5% of candidates, so this is the score you need to get to be in Top Gun, in the best of the best. So that value there, well, that's the mean plus 1.96 standard deviations. The table told us how many standard deviations away from the mean it was, and I was able to do that calculation to work out that cutoff value. Now, how did I know that we would, because the table works at both ends, how did I know this was a right-tailed problem? Well, you've got to look at the context, haven't you? I mean, firstly, we were told up here that we were looking for the value such that the probability that we get more than that is 0.025. And you're not going to let the worst 2.5% of people onto your fighter jet program. Hopefully not, anyway. Hopefully not. So have a little look at the next couple of questions. So that was 5 on page 49. Just have a go at 6 and 7. Now I'm conscious that I still haven't given you a title for this. I haven't forgotten.
So for A on 5, did you just write down 1 with?
Absolutely, yes. So that's just the value I got from the table. And the Z value is the number of standard deviations. In this case, you'd have to go above the mean to get that probability. Petite means small. So we're looking for hats that fit the smallest 15% of people. Sadly, I have the biggest head in North Devon, so it's going to be for the likes of that. The table is really odd. It should be one long table, so it's it's P and then corresponding Z values. That I don't know why they put it in rows. It's I find that confusing. So you're looking up the P value and writing down, I'm using red, the Z value, and then applying that to the context. Now there's a subtle thing here. When you looked up the value in the table, remember that value is for both left and right tail. So because we're talking about a value below the mean, we would be expected to write that value as negative. So the answer to part A is minus the value from the table. So the cutoff for this hat is 1.0364 standard deviations below the mean, and in the context here, that means 57, the mean, minus 1.0364 lots of 2. By all means, have a punt at number 7. So the 10th percentile is the value which has 10% values below it, and the 90th percentile is the value that has 90% of the values below it, or as I've interpreted it, 10% of the values above it. So earlier in the lesson we were using the calculator and looking up the probability in the calculator, and it was giving us the actual value that had that probability either above it or below it, because we were also telling the calculator the mean and standard deviation. Here we're not telling the table the mean and standard deviation. We're just telling it the probability, and it isn't giving us the value then, it's just telling us how many standard deviations either side of the mean it is. So we're dealing, when we use the table, not with a specific context, but with this general normal distribution where we're only being able to, where we can only be told how many standard deviations we are. So the answer to that one, hopefully you got that, the range of life. That's a misleading question because I would have done one, take away the other, but there we go. So what we call this approach is the standard normal distribution. When we look up a value in the table, we are looking up a z value where z is a normal distribution where our reference point is the mean, so the mean is 0 and the standard deviation is 1. So the standard normal distribution is a normal distribution that looks like any normal distribution, but its mean is 0 and the standard deviation is 1. I have to say, you don't need to understand this next bit to answer questions. We've just answered the questions before I explained this. I did that deliberately. And so once we've looked up a value in our standard normal distribution, we then change it back into a value for our contextualized normal distribution, where we've actually got a mean and we've actually got a standard deviation. And this is a sort of coding. If you want to take a normal set of data and turn it into a standard normal distribution, you need to take all your values, subtract the mean, and divide by the standard deviation. That tells you, for each value, how many standard deviations away from the mean it is. So actually, that's the way you go that way. But hopefully I've just demonstrated that you don't need to worry about that. All you need to do is remember that when you look up a value in the page 34 table, it is telling you how many standard deviations, either above or below the mean, a particular value is. And so we actually go the other way. We do the mean plus or minus the value times the standard deviation. So I'm sort of doing my job by showing you that. And there is actually something tomorrow that means we need to be aware of this. But I'm hoping that you can understand how to solve standard normal distribution problems using the sort of common sense approach that I have described. So hopefully most of you made progress with that. So please do have a go at those inverse ones. And then tomorrow in particular is a full-on lesson. But if we get through that, we've got a fighting chance of finishing this part of the content anyway before the Easter holidays.